Right. Thank you so much for the invitation to give a colloquium here. I'm really excited to tell you all about a sort of a broad overview about all the work that I've been doing in this field of applying ideas from quantum information theory to understanding quantum gravity over about the last decade or so. Okay, so let's get started. Let's start with just reviewing the broad understanding of nature that we have today. How do we understand fundamental physics? Well, we have two really successful theories. First, we have quantum field theory, which is a framework to describe local quantum physics at short distance scales. This, of course, has been remarkably successful. It's been tested to great accuracy in different ways, some of its successes being the standard model of particle physics, which has been tested at the colliders and exemplified by the discovery of the Higgs, which is one of the biggest successes in high energy physics. But not just in high energy physics, the same sort of formalism has also been used in condensed matter theory, where it's been used to describe exotic materials such as superconductors and their phases. This has also been a great organizing principle for understanding the different kinds of matter that we can have. Okay, so that's one of our successful theories. We also have general relativity, which describes the classical physics of large-scale structure of our universe. Again, this is a really old theory that has been tested to great accuracy. Of course, the biggest and most relevant one for all of us being something that all of you should be really familiar with, because you guys spend so much time staring at it while you're stuck in Bangalore traffic, the GPS, right? The GPS is famously requires general relativity for it to work accurately, otherwise it would be off by about 10 kilometers every day. But such earthly matters apart, we have much more heavenly successes, such as observing black holes as part of the Event Horizon Telescope and gravitational waves generated by the merger of such black holes. These have been amazing experimental successes over the last decade or so. So, good. These two really successful theories are annoyingly good in some sense. It makes it really hard to discover new physics. So it almost feels a little bit like this famous story that before the discovery of quantum field theory and GR, Michelson is supposed to have said that all of fundamental physics has now been discovered and any new physics lies in the 6th decimal place. Now that would really suck for me because I'm really bad at 5-loop calculations. But of course, we're not in that dire a situation. We still know that there's more to understand at the level of the big picture of physics. And that's where quantum gravity comes in. The important point being that these two very successful theories are actually incompatible with each other. So we can of course use GR and QFT together, and it works great as a low energy effective field theory. We can make predictions such as computing quantum corrections to Newton's law, or trying to understand the cosmic microwave background and the emergence of large scale structure in our universe, and that all works perfectly fine. But this cannot be the complete story. We know that this cannot be the complete story because as a quantum field theory, GR is non-renormalizable. It does not make sense as a complete theory. And perhaps it makes sense that it's quite different from all of the other forces because it's the dynamics of spacetime itself as opposed to the dynamics of some fields living on spacetime. So the hope is we can perhaps find a better unified theory where both of these different ingredients emerge from.
Recording in progress.
Good. So we like to understand the origin of the universe, how the Big Bang happened and so on, regimes where quantum gravity becomes important, and also explain all the parameters we see in our world from some unified theory. So the standard model has 20 odd parameters, and we'd like to make some sense of why we see what we see. And all of this would be great to get from some sort of unified theory, but of course it's been really hard because we don't have much experimental guidance. Testing quantum gravity is pretty difficult, and it's in regimes which are really hard to access experimentally. So what do we do then? So what we've tried to gain guidance from is a theoretical playground, which is black holes. Black holes have served as a really useful playground where we can try to understand how quantum and gravity come together. So how exactly have black holes guided us on this path? The key idea is that of black hole thermodynamics. So black hole thermodynamics is this remarkable bottom-up insight that you can associate an entropy to a black hole so that the total entropy in the universe is given by what's called the generalized entropy that has a contribution from all the quantum field theory degrees of freedom outside the black hole, that's this S out. But in addition, you have a contribution from the black hole itself that's given by the area of the black hole horizon divided by 4g Newton. This is the so-called Bekenstein-Hawking formula for the black hole entropy. And this initially was derived by just staring at Einstein's equations and looking at it and trying to make it look as much as possible as the laws of thermodynamics. You essentially treat black holes as thermal systems, perturb them, and try to see how they behave under such perturbations from equilibrium. And that resembled a lot the laws of thermodynamics with this A over 4g associated with an entropy. This of course made much more sense after Hawking discovered that black holes actually do have a temperature quantum mechanically, and so they should be in fact treated as thermal systems. But there's an alternative way in which you can try to derive black hole thermodynamics, which is using the Euclidean gravitational path integral. This is an idea that was pioneered by Gibbons and Hawking in the 80s, where what they did was try to mock up how we compute thermal partition functions in quantum field theory. In quantum field theory, what you do is you have a thermal circle and you try to compute the partition function of a quantum field theory on this thermal circle of size beta, where beta is the inverse temperature. Now in gravity, of course, you can't do the same thing because you're looking at the dynamics of space-time itself, so you can't just fix some circle. But you can, so what they really thought to do in that situation is try to fix this thermal circle out at infinity, where you imagine that gravity decouples from everything else. So it's sitting at a non-gravitational place far away. There you have a thermal circle of size beta, and then you allow yourself to integrate over all possible gravitational configurations, all possible spacetimes consistent with those boundary conditions. When you do so, you can just now associate an action to each of these configurations and integrate over them. And what you find is there's a saddle point for this integral, which is given by a Euclidean version of the Schwarzschild black hole. It's basically where you take the Schwarzschild black hole and Wick rotate time into a spatial direction. That looks like the following. You start with a thermal circle out at infinity, which then shrinks down all the way to a point, and this point is essentially the Euclidean version of the black hole horizon. So you can use this idea and compute what you think is the thermal partition function in quantum gravity. Once you have the partition function, you obtain the free energy from it, and you can then obtain the entropy. The entropy you obtain is perfectly consistent with this Bekenstein-Hawking formula. It precisely gives you A of the black hole horizon, which is this tip of this cigar, over 4g. However, it's good to point out that while this is some sort of an oracle that's giving us the right answer, it's not so clear what the interpretation is in terms of a Hilbert space. Partly that's because this thermal circle contracts, and it's not clear how to associate an interpretation in terms of a trace over some microscopic degrees of freedom. Another way to say that is Euclidean quantum gravity gives you the right entropy, but it doesn't tell you what the right microstates are. It just gives you some thermodynamic description. So in that sense, Euclidean gravity is a bit of a black box. We don't really know what exactly we're computing, but it seems to give us sensible answers that's consistent with black hole thermodynamics. Okay, so of course, whenever we have some sort of entropy, the history of physics tells us that we would like to associate some sort of statistical explanation to it. It's some sort of microstate in terms of some microstate counting. And this has been the holy grail of quantum gravity, to try to obtain some sort of statistical explanation of such an entropy from some sort of unified theory. And the attempt to do so is interesting on its own, also for the reason that when I wrote this formula, I was secretly hiding a lot of the physical constants that go into this formula. When you restore all of them, it actually has factors of Boltzmann's constant, the speed of light, and h bar. So trying to explain this as an entropy would require combining all the different ingredients of physics that we understand as of now: thermodynamics, relativity, gravity, and quantum mechanics. Right? So it would be something that would really be, it's important for us to understand all of physics in order to be able to reproduce this. Okay, so how have black holes guided us on this path to quantum gravity? The idea that's been really helpful in us trying to do this is holography. So this is a novel feature of quantum gravity which comes about just from asking the following question. The question one asks is, what's the maximum amount of entropy you can store in a given box? Let's imagine it's a spherical box for simplicity. In quantum field theory, we know that the number of degrees of freedom in any particular system scales like the volume. It's an extensive property, right? So as you add, so for example, in a lattice model, you have spins at independent sites and you can choose them completely independently from each other. And so the quantum field theory entropy goes like a volume. However, if you include in gravity, then as you add more and more excitations into the box, it eventually crosses the threshold to form a black hole. So eventually what's going to happen is you have all of these degrees of freedom, they have too much energy, so they're going to attract each other and collapse into a black hole. And you can estimate that the amount of entropy that gas initially had is actually much smaller than the entropy of the resulting black hole. So the best you can do actually for large boxes is actually to just fill it with a black hole that completely fills up the box. So you have a black hole which is taking up the whole area of the whole volume of the box. But we know from the Bekenstein-Hawking formula that its entropy is given by area over 4g. So it's just given by the area, which is just the boundary of the box, as opposed to the volume of the box itself, which is what you would expect from just naively extrapolating from quantum field theory. So this is some new property of quantum gravity, which we don't find in quantum field theory, and something you'd like to use as a guiding principle. So this is what leads you to the holographic principle, the idea that quantum gravity is very naturally formulated in terms of a theory that lives in one lesser dimension. So if you think about a theory that's living in one lesser dimension, for example, here in this picture, you can think about this hologram that has a lot of bits living on the box, on the edge of the box. And this purported theory should describe all the gravitational physics that's happening inside the box. If that were the case, there would be a very natural explanation for why the entropy goes like the area. It's just because it's an entropy in a lower dimensional theory, which is non-gravitational. Okay? All right, so good. That's an idea that was floated around, but remarkably, string theory has given us a precise duality of exactly this form. So it's what's called the ADS-CFT duality between anti-de Sitter space. Anti-de Sitter space is essentially hyperbolic space, which looks like this with a time direction. Here, all the triangles marked in blue have equal area. So as you go out closer and closer towards the boundary, the distances are blowing up, areas are blowing up. And so you have to cover much lesser angular distance to obtain the same area. The effect of having this sort of a geometry is essentially for it to behave like a box. Because of this geometry which grows as you go outwards, essentially what happens is particles can't escape all the way out to infinity, and they're contained inside some region inside the bulk. And so you have some region outside, which is the asymptotic boundary, which effectively behaves non-gravitationally. And the remarkable idea of Maldacena and others was that you can actually find a conformal field theory, which is just some quantum field theory living on its asymptotic boundary, which is exactly dual to the gravitational physics inside this box of anti-de Sitter. So it's exactly a duality of the type which was suggested by the idea of holography, which I discussed in the previous slide, just by analyzing black hole thermodynamics. So once you have dualities of this type, you can actually give precise microstate counting interpretations of the black hole entropy in appropriate settings where you have anti-de Sitter space, or if you have sufficient amount of supersymmetry, which gives you control. In those situations, you can understand the black hole entropy as counting some states in the conformal field theory. That's the full quantum gravity theory, which is the true degrees of freedom, describing the anti-de Sitter space, and you're essentially just counting the number of states in that theory. That's true. This is for this part. I agree with that. Yeah, this was just in the flow of holography. That's yes. But either way, the important point here is that there is a limited sense in which you can understand the black hole entropy in settings where you have like appropriate amounts of supersymmetry or anti-de Sitter space. Either of those. Good. So now, since this gives us this interpretation in these limited settings, a complementary way to approach this problem is to go bottom up, where we try to look at these dualities and try to extract the universal principles that we've learned from this duality, of how this duality works, and then try to enhance our understanding of how the idea of holography would work in more general settings. Right? So going beyond this idea of ADS-CFT so that we can explain other settings like cosmology in our universe or black holes and so on. Okay. Good. So a very natural language for extracting these universal lessons of holography has been that of quantum information theory. This is a set of ideas that's been often encapsulated by the phrase "it from qubit." It from qubit emphasizing the emergence of geometry, it from basic quantum ingredients, qubit. And the idea being that what's really important for the emergence of space-time and quantum gravity is just this quantum information. So the poster child of this set of ideas is what's called the Ryutakinagi formula. The Ryutakinagi formula is a connection between entanglement and geometry, which says the following. So we first want to compute the entanglement entropy of a subregion in the CFT. That means looking at a particular time slice on the boundary of ADS where the CFT lives. That gives you a state living on the conformal field theory. We then partition it into two parts, this interval capital R and everything else, which is R bar. And we then try to, then we look at the reduced density matrix on this subregion and try to compute its von Neumann entropy. That gives you a measure of the amount of entanglement between capital R and R bar. When you, that's this left-hand side, S of R. And the proposal of Ryutakinagi was that this is given by something very much like the black hole entropy formula. It's an area over 4G of the surface gamma R, which is the minimal surface anchored to the endpoints of R. Right, so this surface, plus the entropy of bulk matter fields in the green shaded region, little r. So this is very much like what we found in the context of black holes, even though there's no black holes here. So here, essentially, this minimal surface is behaving somewhat like the black hole horizon. It's giving you some sort of partitioning into degrees of freedom, some of which are outside and some of which are inside, and the entropy, the generalized entropy is computing the area of this surface plus the entropy outside. And now because it's just an entanglement entropy, we have a state counting interpretation for it. And it's basically just counting the states in the CFT. If you follow your nose with this idea, you also land on the idea of subregion duality. Subregion duality is the idea that the bulk data in region little r is completely captured by the boundary data in capital R. So ADS CFT was a more general duality which was telling you that ADS equals CFT, all of ADS equals all of CFT. This is now a much more fine-grained picture where you now understand that some part of ADS equals some part of CFT. Yeah. Yeah. This thing? Uh-huh. Yes, yes, yes.
On the right hand side, you'll see all these. So there's a particular precise statement about when.
Good. So I think what you want to do is, so in order to phrase this duality, you want to have some sort of map between bulk and boundary, and you want to say, so in order to have this map, you first need to understand how to think about the bulk. The only way we know how to think about the bulk at this point is in terms of some semi-classical description where you pick some background and you have some excitations on top of it. That's a sort of a limited set of states which can be mapped to the CFT, and then you can compute the entropy and map and match with this formula. You can do more. You can also try to patch in other backgrounds in this, so you can make a sort of larger subspace of states where you have one background plus excitations and another background plus excitations, and this is okay as long as you don't have too many of them. So you can also try to understand it in that sense. Yes, it's this would then be interpreted as an expectation value. So it's going to be an it's basically you'll have some probability distribution over all of these geometries, and you'll have to take the weighted sum over all of them. Yes. Exactly. Yes.
So how, is there a precise boundary between when this is valid?
That's a good question. So the general story, so I think what you're asking is related to this question of the following, which is that the sum of these things seems to be giving you something that doesn't care about, say, the effective field theory that you're setting up in the bulk, right? You can change the renormalization scale, for example, and things here will change. The entropy will change. Yeah, I think it's in the same sort of spirit. I just mean that that's one example of what you would say, which is that you can then move terms from here to here, but somehow this sum seems to have some more robust meaning. And but I think this sum over geometries is also in the same spirit. Like if you have a sum over you can have two different what's called code subspaces, where you have one of them has many geometries with bulk states on top of them, and the other one doesn't. Let's say it just has one of them. These are two different effective field theories, and the claim here is that the entropy here, since it's just one thing, as you said, like suppose you can fit a particular CFT state in both of these subspaces, then you would say that you can compute it in either of those and it should match, and it's going to match in different ways, and it's roughly in this Susskind-Uglum way where terms are going to move from one side to the other, but overall the sum has to stay the same. Yeah. It's not so clear. Like if you have a high energy typical state, yeah, it's going to have a black hole. So the exterior, like to a great extent, we understand is just given by the Schwarzschild black hole. So you and for the purposes of computing the entropy, that seems to be. It's a finite entropy, so it'll depend on like what's behind that. But let's say it was just a pure state, then of course we know that the entropy is just zero. Yeah, it'll depend on what the details are. Like suppose you had a thermofield double or something like that. So there's another boundary, then you'll just compute the, yeah. But I agree with you, like this only makes sense in some limited sense as an effective field theory statement on the bulk side, but the left hand side makes sense beyond that. So ideally what you'd like to do is, even on the bulk side, have some complete description, like some UV description where you include all of the states in terms of some quantum gravity degrees of freedom, and you can make sense of the right hand side in all states, and then it would just be a one-to-one map, like where you don't have to worry about this effective field theory. But we're not there yet. So at this point, it's just an effective field theory statement. That's also true. At this point, like what I'm saying here is essentially tested until order 1. Order 1, yes. Yes. That's right. Okay. Good. So yeah. So we have this map between between regions, between this interval on the boundary and this green shaded region, which is called the entanglement wedge of this boundary region. And all of these things can basically be understood abstractly just by thinking of ADS-CFT as a quantum error correcting code. The way a quantum error correcting code works is you have some set of qubits which you want to capture. This is also how quantum computing works. You have some set of logical qubits, which is where you want to do the quantum computation. But since there's always going to be errors, there's always going to be errors in the lab, you want to map them to some larger set of physical qubits so that it's robust to any of these errors. So in this case, we should think of the bulk as the logical qubits, which are being mapped to the boundary as physical qubits. And the way, and then the idea of quantum error correction is, even if I lose all the physical qubits that are in the region R bar, which is the complement of this region, I still preserve the green shaded region in the bulk. So a lot of the logical qubits are still preserved, even if I coarse grain over a lot of the physical qubits and they've been lost. So this idea of quantum error correction makes it sound very universal. This is just one way of understanding how ADS-CFT is working, but a quantum error correcting code is a much more general idea than ADS-CFT. So presumably such ideas can be useful to understand how quantum gravity works more universally. And you can also show that any quantum error correcting code actually has something like a Ryuta-Yanagi formula, which is shown in this paper. Okay. Good. So that brings me to tensor networks, which are a particular toy model of holography. They are a particular instantiation of this idea of quantum error correction. And in particular, we're going to look at random tensor networks, which exhibit all of the previously stated properties, that is, the Ryuta-Yanagi formula and subregion duality. And similar models have been used in other fields, like quantum information and condensed matter, to model various aspects of ground states of systems or thermal states and so on. The idea of a tensor network is that we build up a state on the boundary using some sort of contraction of tensors. So more precisely, we start with a graph G, which is specified by its set of edges and vertices. And this defines a boundary state as follows. At each of these vertices, we pick a Haar random state. So for example, here we have two of these vertices. Tx and Ty are the random states that we've picked at each of these vertices. These states live in a tensor product Hilbert space of these 3 bonds. So we imagine that each of these has some bond dimension d. So then the state lives in a Hilbert space of dimension d cubed. We then look at what the edges are. So the edges are obtained by projecting these states onto a maximally entangled Bell state. So this xy represents a maximally entangled Bell state, which we're projecting these particular bonds onto, and that has the effect of connecting x and y by an edge. So that's what we're doing in this big graph here. Now we have two options. We may or may not include these yellow dots. These yellow dots should be thought of as uncontracted legs that are going out of the plane, that are coming out. If we don't have them, then every leg has been contracted and we're left with open legs at the boundary. So this prepares a boundary state. On the other hand, if we have these legs, then we have a map going from the bulk to the boundary, which is how we want to think of ADS-CFT as working. No, the Tx is more like the analog of the UV degrees of freedom in the bulk. So if we can imagine that one of these legs is chosen to be a bulk leg, which has smaller dimension, and these legs are all going to be contracted. So the in the plane legs are all contracted, and the Tx is partly a state of those things. In addition, it can have these legs going out in the bulk, where you can input the QFT state. Sorry? Oh yeah. These dots that we have, those are the ones which are legs going out of the plane, and those are where you would input a QFT state.
So that will be the bulk.
That would be the bulk state.
And so what you mentioned that you said that's like
Yeah, roughly we're going to take d to be e to the 1 over g. Yeah, that's right. Good. So the interesting thing to note here is that the role of geometry is literally played by entanglement, right? So the building up of edges, which is all that is determining all the distances in the graph and all the areas, is literally done by projecting onto Bell states, and so entanglement equals geometry in this context. Okay. So we have this model. No, it's the generalization of that. So imagine you have 0, 0 plus 1, 1 plus 2, 2 up till dd, something like that. So it's just something which will correlate the state of these two legs. So you're projecting onto them being in the same state essentially. Okay. Good. So you can then use this in the limit of large bond dimension where we gain analytic control. As d goes to infinity, as Chetan was asking, d should be related to e to the 1 over g, and so that is related to g going to 0. And in this limit, one can check that the random tensor network actually exhibits a Ryu-Takenagi formula and subregion duality. So it's exactly of the type that we found in ADS-CFT. Okay. And not just that, we also find that these random tensor networks are only approximate quantum error correcting codes. So everything I said before about Ryu-Takenagi formulas and quantum error correction was related to exact quantum error correcting codes. But we also expect that ADS-CFT actually works like an approximate quantum error correcting code because of non-perturbative effects that come from gravitational instantons. And this is actually crucial for describing things like entanglement phase transition. So if we, instead of picking a single interval on the boundary, if we have two intervals, then there's two possible candidates for the minimal surface. There's either the disconnected surface, which is this green surface, or the connected one, which is the orange surface, gamma 2. Depending on the size of the intervals, there's going to be a phase transition between which one is the shorter one. And so yes. I mean that the entanglement wedge is disconnected. So the entanglement wedge in the first case is just the union of these two disconnected pieces, whereas in the second piece, it's completely connected. Yes. It just means that there's some parameter. So here, d is the parameter that's going to control the errors. So in the d goes to infinity limit, there's a exact quantum error correction. But when you start accounting for finite d corrections to it, then you realize that it's not an exact quantum error correction. So when you erase some part of the boundary, you don't keep all of the information of the bulk. It's only up to an approximation. And that is a very important effect that is very useful when you try to describe these phase transitions. There is no diffeomorphism invariance in this. So the random tensor network lacks diffeomorphism invariance, but it's not going to affect the relation to gravity. What we're going to relate it to gravity is, its relation to gravity is on a much more coarse-grained level, and diffeomorphism is a much more continuous thing. So you're not going to recover diffeomorphism invariance. You're also not going to recover other things like the Hamiltonian constraint and so on. But the idea is this is some sort of toy model of how ADS-CFT works at a kind of coarse-grained level, which is sufficient to still teach us things about ADS-CFT. So it's not going to be, I'm not going to say that this is quantum gravity. That's not the case, but it's going to teach you something about quantum gravity. Good, that's because of ADS-CFT. You wouldn't. Well, at this point we were still talking about like this is still a hyperbolic network, which is basically a coarse-grained version of ADS. It didn't need to be that. We didn't. Yeah. So as I was saying, like this is. Yeah. So what we're going to say, I will get to this. So what I'm going to say is essentially the way the calculation happens in the random tensor network is very closely related to how calculations go in the gravitational path integral. This you can think of as some sort of coarse-grained model for how gravity functions. It's not going to give you any of the continuous aspects of gravity like Einstein's equations or the Hamiltonian constraint or anything of that sort. So in that sense, it's not gravity because it's not going to give you the perturbative stuff. But it's going to give you some of the non-perturbative stuff, such as the instantons that you find in the gravitational path integral. Yes, that's right. Yeah, that's right. That's right. That's exactly correct. I mean, you still want diffeomorphism invariance because even if you fix that induced metric, there's still diffeomorphisms on that induced metric, which are still pure gauge.
That's the kind of sort of like a classic kind of, what you're interested in the Hamiltonian constraint.
Yes. You're not going to get the I mean, this is largely going to be related to time-independent situations where you don't talk about any time evolution at all. But I think I would still say that, I mean, you still care about other...
Yeah. I think that, that's kind of related to this thing of the CFD side. There's, you can do all the cases.
Yeah.
The, entanglement on the right-hand side is for some pizza time.
Yes. Yes. I think I agree with that. Yeah. I will say a little bit about how exactly we map this to gravity. But at this point, you can think of it as a toy model for how ADS-CFT works. Let's just keep it at that for now. Okay, sorry, where were we? Yeah. So in this picture, we're trying to describe this entanglement phase transition, and the random tensor network precisely shows this. You could in principle. So you could imagine that you have, so tensor networks are also useful in condensed matter for actually computing correlators. Like you actually have a true approximation to the ground state, for example, of some theory, and you can compute correlation functions using that. So the random tensor networks, you can try to do the same thing. What you'll find is essentially that correlators can be computed either on these bulk legs, or they can be mapped to the boundary and they're computed by some boundary correlation function, and they are in exact duality with each other. But here we're modeling the theory very coarsely, right? So we just treated these tensors as random. If you really wanted to care about exact correlation functions, you'd have to care about what the exact tensors are that would build up the ground state of that particular theory. Here we're saying whatever it is, it's sufficiently random that for the purposes of computing entanglement entropy, it won't affect the answer. So no matter which theory I talked about, I would still get the same answer. Yes. But if you had full control over how you could build up this tensor network for a particular theory, you could compute the correlation functions. Okay. So this seems to suggest that there's some connection between the mechanism by which ADS-CFT works and the mechanism by which these random tensor networks work. So how much can we really learn from this toy model? How far can we push the limits of this connection, this qualitative connection between random tensor networks and gravity? So when you try to relate them, yes. Yeah. No.
So fair to think of all the possibilities of how that can be
Yes.
Or maybe not the researches of Holography
Yes.
as a sort of basis for the eigenstates around
Yes.
the background.
Yes. You should think of that as the QFT, like, yeah, all the possible states you can put there are all the semi-classical states on top of this background, basically. It's the QFT state, yeah. Okay, so when you try to relate the random tensor network to gravity, there's an immediate tension you find, which is related to something that Chetan was commenting on, which is that in random tensor networks, when you try to compute the Renyi entropy is defined as follows. It's essentially a one-parameter generalization of the entanglement entropy, the von Neumann entropy. And essentially, you can think of it as probing the entanglement spectrum at different temperatures, which are determined by this parameter n. And in the n goes to one limit, you recover the usual entanglement entropy. This quantity for the random tensor network turns out to be completely independent of this parameter n. And this is basically due to the maximal entanglement that we have between the bell pairs that form the bonds of this network. Now, this feature is quite unlike gravity. In gravity, we have predictions from ADS-CFT which tell us that the Renyi entropy should depend non-trivially on n, on this parameter n. For example, in the ground state of a CFT. And in fact, in Renyi entropy, there was a proposal that the Renyi entropy in ADS-CFT actually satisfies something like a Ryuta-Yanagi formula. It's given by the area of the minimal surface in a deformed geometry. So there's a very particular way in which you deform a geometry by adding what's called a cosmic grain, and then try to compute the area of a minimal surface on that geometry. Now, since, as we discussed, like the RTN just has a particular geometry, there's no equivalence of this dynamical response that you expect in gravity. So it's lacking this piece of dynamics which which gravity has. Okay, so but that then suggests a particular cure for this tension, and the cure is to just think that these gravitational, there are in fact gravitational states which behave just like random tensor networks and exhibit a flat entanglement spectrum where you just restrict all the fluctuations in the geometry. So instead of, yes. The randomness is not important there. It's also true of, say, the happy code, which is an exact quantum error correcting code, or the feature that's missing here is, essentially what I'm going to say is that the thing that would have this non-flat spectrum is like a superposition over these random tensor networks as opposed to a single random tensor network itself. So the same thing. Exactly, like you have some sort of fluctuations in the geometry, and once you include those, then you would find that you'd find this non-trivial Renyi entropy. Yes. Yes. Sure. Yeah. Yeah. Yes. 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 Yeah. Yeah, yeah. Yeah.
So what is the general direction? I know it reminds them, the so on, but still.
Yeah.
It is a bit of an issue, but you have much of technique that, because it's all in the sphere of ideas.
Yes.
One really doesn't have a guide. Where is the real guide going from?
So, in the history of physics, very often that guide comes from experiment, of course, right? Like most of our theory is guided by that. Unfortunately, as I was saying, we don't have that much experimental guidance in this regime where we want to understand quantum gravity. And so instead, fortunately, it has been the case that it's been really hard to find a theory of quantum gravity. So just theoretical consistency itself has been a great way to lead us somewhere. So just these proposals and consistency and so on is just some way in which we're trying to find, we're trying to shoot down ideas, right? So we could come up with many different things, and then many of them are just inconsistent among themselves, and we're just trying to look for a set of ideas that are seeming coherent among themselves. Yes. 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 That is a fair statement. So this is exactly the quantum generalization of the information theory ideas that came from Shannon. Yes. Yes. Exactly. Exactly. So in that context, like, yeah, there's nothing that violates, say, a Bell experiment, right? So there is more to quantum than just that, but it's true that it's a generalization of the usual classical Shannon theory into the realm of quantum mechanics. Yes. Yes.
Can we then go to the computer and then do some simulations and all, and hope that someday we will be getting such photographs that actually see this kind of behavior instead of somehow.
You mean for the dualities?
Whatever. I mean, whatever are the gold standards in this.
Yeah, so certainly you could imagine testing the ADS-CFT duality or something like that on the computer, right? There's versions of this which perhaps have been tested. So there's like lower dimensional models of this sort of duality have been tested on like quantum computers at Google, right? So you have these predictions from ADS-CFT calculations for how the gravitational description helps you understand some things on the boundary theory, and there's some concrete prediction that you get from it, and then you can go out and test it either in an experiment or on the computer, and that is something that you can very robustly check. There's other predictions like in like for example in the four-dimensional duality where there's a super Yang-Mills theory which is dual to the bulk theory. You can try to compute all sorts of things, and there's some prediction from the gravitational side which completely agrees with the calculation that you can do. So there's a lot of tightness in this, that these things fit together. So while they're conjectures, there's a lot of evidence for these conjectures. Yes.
Does that qualify as verifying? What is the context in which this comes up? I will imagine that if there is a conditionality,
Yes.
then this is applicable.
Yes.
Then you will be able to test this duality.
Yes, indeed.
Has it been tested?
So the instance I was talking about was like, for example, in the two-dimensional version of this, there's a bulk, where you have a two-dimensional bulk. There's a one-dimensional theory on the boundary, which is one of the instances of which is what's the SYK model, which is a condensed matter model that you can do computations with.
I was thinking more in terms of an experience,
Yeah. So I mean like the SYK.
which have tested.
Yeah, so I mean, it depends on whether you call it experiment. Like you can simulate it on a quantum computer. Like, would you count that as an experiment? Okay. And then I think it hasn't been.
Flat out say that's
Okay.
It's not just
That's good. Yeah. So there's certainly other experiments where it's been actually, you've tried to do it on as an experiment itself, but I don't think they've gotten anywhere near the level that you need to test any of this. But it's an in-principle thing that can be done. I don't think it has been done yet.
it's a fair answer.
Yeah. Yeah, I think the status is that it hasn't been tested in an experiment in the sense that you mean it. Yeah. Thanks. Any other questions? Okay, good. So getting back to this, so the fix that we proposed was that instead of considering states which have a wide spread in the area of the minimal surface, we can instead consider approximate eigenstates of the area of the extremal surface. So in this figure, I'm trying to plot the wave function as a function of the area of the minimal surface. And this sharply peaked function is, you can think of as an approximate eigenstates. It's very close to being a delta function. Whereas semi-classical states that are usually prepared in using the gravitational path integral have this wide spread, and they're more like coherent states. Sorry. So the x-axis here is the area of the extremal surface. So it's just one parameter that you're evaluating in all of these geometries. And the y-axis here is like the wave function. Or you can think of it as the mod psi squared, for example. So what it's saying is essentially if you look at the gravitational state and you try to evaluate the area of the extremal surface, there's some highly likely area that you'll get, but there's always fluctuations around that of order square root g. Whereas in these fixed area states, it's much smaller, it's order g or less. So it's sort of analogous to working in the microcanonical ensemble versus the canonical ensemble, where in the microcanonical ensemble you have a very sharp window, and in the canonical ensemble you have some spread in the spectrum. In this thing, so if you took an exact eigenstate, then you don't expect any sort of semi-classical description at all. It's because it's like in thermodynamics. It's like where you start probing the fact that there's discrete number of states. So as long as the spacing is sufficient so that it's not exponentially small, then you're good. But as soon as you start probing the discreteness, then you don't have a semi-classical description. So you still want an exponentially large number of states, and that can happen as long as you have a polynomially small window, and that's fine. Okay. Yes, so we're still working in some sense as in some canonical quantization language. It's like we're still thinking of the low energy degrees of freedom. We don't care about the UV because of this fact that we're not sensing the discreteness and the microstates as such. So there's still some coarse-grained description in terms of a geometry. Yes. And these can be prepared using the gravitational path integral, so we trust that because we're not in this regime where we're probing the discreteness.
So hello, can I ask you a question?
Yes.
So when you are talking about this fixed area state,
Yeah.
so are you keeping Newton constant fixed, zero here, or it is some finite value?
Sorry, what am I keeping fixed?
Newton's constant.
Oh, Newton's constant.
Are you keeping it to?
Okay, yeah. And here I'm thinking of Newton's constant as some finite thing. The spread that I've shown here in the wider thing, which is the coherent state, is of order square root g. So of course that's only finite if g is finite. Similarly, even this sharply peaked one, we're always going to do calculations in the g goes to 0 limit, but the distinction between these is very important. The fact that you have very sharply peaked wave functions in one case versus a slight spread in wave functions in the other case.
Okay.
Does that answer the question?
Yes.
I have a lot to go. Okay. I can just. Yeah, so the idea is, so there's some particular way, in order to compute the Renyi entropy, you deform the geometry in a very particular way. It's essentially like adding some function of the area into the action. Now, what that generically does is it shifts the saddle from the peak of the wave function to some part of the tail of the wave function. But if the tail is so tiny that you've made the wave function only have support on some really small piece which is sharply peaked, then there's no place for the saddle to shift to, and so the fixed area state results in even after adding this deformation, it doesn't really shift the saddle much, and you end up with the same geometry. Whereas in the other case, it does shift the geometry. Okay. Good. So the idea is what the random tensor network is modeling is basically these fixed area-like states. These are essentially analogous to position eigenstates. So in quantum mechanics, we of course use position eigenstates all the time, even though they're not very semi-classical. Reason being, if you have a very small window in position, of course you have a very widespread momentum, and so they're not going to be classical in any sense. Coherent states, on the other hand, do look classical. So even though we're interested in perhaps some semi-classical calculations, we can always use this as a basis to do these calculations. It's analogous to that. Okay, so our proposal was that the random tensor network is essentially modeling this fixed area basis, and by superposing different tensor networks, that's like superposing different geometries with appropriate weights, you can now have this area fluctuation, which will result in this dynamical back reaction that shifts the saddle and accurately reproduces gravitational answers, which are n-dependent. So in this particular example, the top geometry has a minimal cut, which is just 3 legs, whereas the second one has a minimal cut that's 2 legs. So depending on what these weights are, as a function of n, the saddle will shift from one to the other, and you'll find a Renyi entropy that depends on n. If you add more and more terms, it will become more and more continuous and look much like the gravity answer. It's representing basically the Ryutakinagi surface. So if you want to compute the entropy of one of the sides, then the minimal cut is telling you what the entropy of that side is. So the minimal cut, so it's basically given by 3 times log d or 2 times log d in these states. But now we're taking a superposition, and the Renyi entropy will change. Okay, good. So let me just give a brief explanation of how and why. Yeah. No, this is a global state. So this is like defined on R and R bar both. So in principle, you could have some more complicated geometry and so on. It'll be a global state that you're defining, and you're trying to fix the entire induced metric on that slice. Yes. Yes, and you can compute these weights. You can compute these weights using the gravitational path integral. It's basically like the Hartle-Hawking wave function. That depends on the details of the theory. So yes, in principle you should, but I don't think this has been worked out in any detail. In principle you should. Okay, good. So let me just tell you briefly how exactly this relation between fixed area states and random tensor networks works. In the random tensor network, we're trying to compute Renyi entropies, and Renyi entropies can be computed by the so-called replica trick. So in the replica trick, you take n copies of the random tensor network and glue it together in some particular way. So you glue it trivially on R bar and cyclically on R. Then you do the average over these Haar random unitaries at large bond dimension, and there's a standard result in math called Weingarten calculus, which tells you that the average over Haar random unitaries is actually pretty simple. It's given by a weighted sum over permutations of these n different copies. So essentially what's going to happen is you have some boundary conditions and you have lattices with spins that live in the permutation group. So it's kind of like an Ising model, and the random tensor network in this large bond dimension limit has a Renyi entropy that's given by the ground state of this model. So here we have a simple example where we have just one node in the network, and we want to compute this entropy, and depending on what the size of these different areas are, the dominant permutation that goes in here is either the identity or the cyclic permutation. So you either extend the red domain inwards or the blue domain inwards. So that's roughly how the calculation goes in the random tensor network. Now the reason this matches very well with gravity is because you can now look at gravitational fixed area saddles. These fixed area saddles are geometries that you prepare using the path integral, and then glue many copies of them together to compute the Renyi entropy, where these different vertices are essentially the surfaces, the competing surfaces that we had in the previous picture. So now once you have these different surfaces, there's different ways in which you can glue together this picture. So for instance, here is one way in which you can do it, where you just glue together 2 trivially, 3 trivially, 1 and 4 swap with each other, and so on. And what you can show is there's a one-to-one correspondence between the ways in which you can get saddles from this calculation, which is the gravitational calculation, and the random tensor network calculation, because each of these is counted by permutation. So here, for example, we have this particular permutation, which determines the pattern of gluing in the bulk. So it's not very theory sensitive. So here we're assuming, of course, that the theory is like Einstein gravity plus small corrections. In that context, it's just dominated by the areas. You can extend it to higher curvature theories, but then you have to just, okay. Good. So this then tells us that the way in which the gravitational path integral is computing entropies is very closely related to how the random tensor network is. And that gives us a complementary Hilbert space perspective for these results that we obtained using Euclidean gravity. Okay, so let me quickly talk about some applications of this idea, this connection between random tensor networks and fixed area states. So the first application I can discuss is black hole evaporation. So Hawking essentially showed that a black hole evaporates into thermal radiation and apparently loses information of how it was formed. This is what's called the black hole information puzzle. And the puzzle is that since you've got just thermal radiation, you've lost information because you started with a pure state but end up with a mixed state. Now in a unitary theory of quantum gravity, there must be some mechanism to bring out all of this information, but this seems impossible with a semi-classical description of the interior. So a toy way to understand this is this toy picture of Hawking radiation as coming from entangled particles, where one of the particles falls into the interior of the black hole and one goes out, carrying away energy from the black hole. In order for the horizon of this black hole to be smooth, you have to have a particular pattern of entanglement between these pairs when they're near the horizon, so that it resembles the Minkowski vacuum. in order for that to happen, it must be the case that all of these entangled particles that leave the black hole are constantly increasing the entropy. So there seems to be a tension between the semi-classical description of the black hole interior and having a unitary S matrix for black hole formation and evaporation. So this was what was called the idea that there's a firewall sitting at the horizon, which has some complicated dynamics, and you really need to understand these complicated dynamics in order to recover the unitarity of this theory. And for a long time, people really believed that you'd need a complete theory of quantum gravity to derive this fact that the entropy goes up for a while and then comes down, which is called the Page curve. But fortunately or unfortunately, it turns out that there's a semi-classical calculation one can do, which precisely gives you this Page curve. So let me say how that works. So essentially, what Page did back in the day, in 90s, was basically the simplest random tensor network calculation. He just considered a random state and partitioned it into two parts. Some legs were called R, some were R bar, and he estimated the entanglement entropy between these two systems. This is, of course, exactly just like a random tensor network. You can do the calculation using the same methodology for the Renyi entropies. And you can, in fact, redraw this calculation in a very suggestive way that looks a lot like the bulk geometry, which we're trying to discretize. So we can consider the situation where we have a lot of this radiation that's escaped into a box that we've kept far away from the black hole. Those things are entangled with the interior of the black hole. And we model the interior of the black hole as a gigantic random tensor. So we think of this random tensor as having legs entering in because of entanglement with the box of radiation. And there's other legs going out, which represent the area of the horizon. Now, in a random tensor network, there's really no distinction between entanglement and area. As we said before, entanglement really defines what geometry is in the random tensor network. So the calculation here should treat these orange dashed lines pretty much democratically with these black lines, which correspond to the area of the horizon. And just like we found in other more mundane situations, there's going to be a phase transition depending on whether there are more orange lines or more black lines. So when there's more orange lines, eventually the minimal surface is going to sit at the black hole horizon. And the way the calculation goes for the Renyi entropy is that we were trying to do a cyclic permutation on the box, but that cyclic permutation gets extended into the interior of the black hole, just like we saw before. This is the idea that there's an island for this box of radiation, which applies the same sort of replica trick into the interior. So this box is sitting very far away from the black hole, but nevertheless trying to compute its entropy leads to some sort of effect in the interior. Okay, so this very simple random tensor network calculation was very prophetic. And although it took a long time for us to realize this, but in hindsight, it was pretty straightforward from the fact that there's a connection between random tensor networks and fixed area states. So eventually we found these novel gravitational instantons, which are called replica wormholes. The RTM calculation is essentially Page's calculation. That was like in the 90s. So it's just that he didn't phrase it in the same language. It was like the dumbest random tensor network calculation, so he didn't need to phrase it that way. But if he phrased it in terms of computing the Renyi entropies, then it was something which was basically a random tensor network calculation, and all he had to do was map it to how that relates to gravity. In principle, this could have been done before ADS-CFT or whatever, so it didn't have, but yeah, it of course took a lot of insight to actually figure out these gravitational instantons. Yes, it's a single vertex, exactly. So this is like a very dumb one where you have one vertex and all of these edges, and that's it. Yes, and it's a really coarse description because I'm treating the entire black hole interior as one vertex. It's like a gigantic random tensor. Yes. Okay, so once you add in these instantons, you find that for a while the entropy goes up, but eventually these instantons kick in where you have this swap operator applied into the interior, and that gives you a decreasing entropy and finally gives you this page curve. This is something that was computed precisely using semi-classical methods, and we never needed to access quantum gravity for this. This is truly remarkable, and yet in some sense it's just another example of an entanglement phase transition. These entanglement phase transitions have been really well understood by just decomposing all of these semi-classical gravitational states into fixed area states. Just like I said before, we just think of any state as a superposition over fixed area states. This actually allows us to compute the page curve, and not just that, it also allows us to compute order 1 over square root g corrections at the peak of the page curve. So it smooths out the page curve in some way. Okay. So what you do is you have a non-fixed area state which you decompose into fixed area states, and then try to do the calculation there and use the answer that you know from fixed area states to then get some answer for this more general state. So for a fixed area state, you wouldn't have these order 1 over square root g corrections, but for a non-fixed area state, you do end up having these because of the fluctuations, like because of the superposition over fixed area states. Okay, good. So how much time do I have? Oh, it's over. Okay, sorry. This one is misleading. I can try to wrap up pretty quickly. Yeah, exactly. So much of what I'm going to say after this will be related to the other talk, so I'll probably push it to that. So let me just quickly try to summarize. So there's just one thing I wanted to say about this, which is that these calculations have this shortcoming that we needed to collect all of this Hawking radiation in a non-gravitational bath. And instead, what one would like to do is to try to compute this, to try to collect it in the gravitating region and compute the page curve in that setting. And to address this, there's been a proposal by Busso and Pennington for entanglement wedges of gravitating bulk regions. So here's one picture where we associate a bulk region little a, and there's an entanglement wedge, which is basically given by the convex hull of this region. This would be a way to address this issue that we can also compute the page curve in appropriately gravitating regions. And using these ideas of converting random tensor networks, random tensor network calculations into gravitational calculations, we can actually derive this in, at least in time independent settings, by just translating this idea into random tensor networks and then using this engine of converting random tensor network calculations into gravity. So we have a derivation of this using that. Okay, so let me just very briefly say what else we can do with this. The broad idea is going to be that we looked at simple things like the entanglement entropy. We can look at other measures of entropy or other measures of entanglement, other quantum information measures, and try to see what their holographic dual is, and use the fact that the random tensor network calculation is very controlled to obtain some answer for gravity. I'm not going to go through all of the details. Some of this will be discussed in my technical talk, but there's various quantities where the gravitational dual was very poorly understood, and what we were able to do was first do the calculation carefully in the random tensor network, then use this engine of trying to convert random tensor network calculations into gravity to find the correct answer for gravity. And so 3 of the examples I was going to talk about is the Renyi entropy, the entanglement negativity, which is going to be the focus of my technical talk, and 2 quantities that compute the entanglement wedge cross section, the reflected entropy and the entanglement of purification. You can ask me more about it later if you're interested. So let me just give some outlook for what we can do with this in the future. The key ideas that I used here were the Euclidean gravitational path integral plus quantum information theory, both of which are very universal tools for understanding quantum gravity. And this fixed area states tensor networks connection has helped us gain a lot of mileage from using these 2 ideas. And importantly, these 2 bottom-up ideas do not explicitly realize on either ADS or CFT. And so one would hope that you can push the boundaries beyond these limits and try to understand more general settings like cosmology or black holes in our universe. That's sort of where we want to go with this. In order to do that, we need a much better understanding of the bulk theory and the dictionary relating bulk to boundary. And there's still a lot of open questions, many of which were pointed out here, one of them being time dependence. There's also diffeomorphism invariance. The description of the black hole interior is still unclear. We have other situations like closed universes. An important feature that I used in many of these calculations was open boundary legs, where we could compute entropies. In a closed universe, you don't have any open boundary legs, so we need to make sense of how to think about this. There have been claims of one-dimensional Hilbert spaces for closed universes and so on, and the situation is pretty murky in that language. So let me summarize very quickly in the form of a limerick. The impact of geometries being integrated along with a QI perspective is understated. Run the RTN engines, go bottom up with a vengeance to get results like the page curve much awaited. Thank you. I was actually, oh sorry, if I had more time, the thing I was going to say is disclaimer, I wrote this and I didn't use ChatGPT. Indeed. Yes, I knew that question is going to come, yes.
Most of the questions inspired
Yes.
already seen in semi-classical terms. Sorry, I have to leave.
Okay.
Catch up about
Okay, sounds good, thanks.
Very nice.
Thank you. No worries, yeah.
Recording
Yeah.
stopped.
Actually,
For that one, which I didn't know that the fact that page had
yes. So, I mean, okay. I think you're right. The part which I wanted to talk about, which I had to skim over, was largely the places where the random tensor network fixed something that was wrong in the gravitational calculation. So if I can just briefly mention this. So in the Renyi entropy calculation was done in 2013 by Lukowitz and Maldacena. This was something where there was an expected gravitational answer. That gravitational answer you can try to test using this random tensor network idea. And what you find is that for n greater than 1, the answer that they got was correct. But for n less than 1, the answer that they got was wrong. So here's a plot of their prediction, which is this sharp kink thing, and the smoothed out blue thing, which is wrong at leading order in 1 over g. So the problem was with the analytic continuation that they proposed, and the way to fix it is by doing this thing where we decompose things into random tensor networks and test it. You can then test it in toy models like JT Gravity, this PSSY model and so on, and you find that precisely you need this modified proposal that we proposed in order to get the correct answer, even at leading order in 1 over g. So even though there was a prediction for what the answer should be, it was wrong. Another situation that I'll talk about tomorrow is the entanglement negativity. There was a proposal from the CFT and from the bulk for what the calculation should give you. It was supposed to give you this entanglement wedge cross section. And from the tensor network, we found that the saddle looks actually very different, and you find a saddle of this form. That only came about from taking the random tensor network, computing the answer there. For example, in this particular case, what was assumed in the gravitational calculation was replica symmetry. This is a very standard assumption for any entropy. It just turns out to be false for the negativity. And that was something that you could see from the tensor network calculation, and then go back to gravity and test it. And you find that precisely this saddle should dominate the answer. So these are situations which I unfortunately had to go through pretty fast, where they are instances where the random tensor network was actually predictive and not just like fixing it in some way. Yes. Yeah. Yes. So the way we think about it is like in the Euclidean path integral, you can think about, like in ADS-CFT, we normally think about preparing a state using some Euclidean path integral. So let's say in the thermofield double or something. So we have some boundary conditions at infinity. And in addition to that, just like the Hartle-Hawking state, we specify some metric h on this boundary condition. And the action of this solution tells you what the wave function psi of h is. And so psi of h is just e to the minus I of this h, of the g h. The random tensor network? Oh, fixed area states, yeah.
Fixed area space, so the idea would be that the wave function is specific.
Yes.
And then you have some statements about what kind of h is.
Yeah, exactly. So in the fixed area case, you're only specifying the area here. So you don't specify all of h, you integrate out everything except that parameter. But you could also just forget about fixed area, you just think about fixed induced metric states, let's say. So you have this fixed h that you specify in some gauge invariant way, and then you can compute the wave function using this. Now this gives you a basis in which you can write any state. This is just like some insertion of the identity there. So it's just some basis in which you're expressing this as a superposition. So there's a very concrete way in which you can compute this wave function.
only a wave, it's a wave function that you're specifying.
Yes, yes, yes. It's a wave function in that basis. Yes.
But that exists in the logistics data.
Yes, you can. Once you have this, then you can use this for time evolution, for example. In principle, it just hasn't been done in practice. Okay. All right. Yeah. Thank you.